Yeah, thank you very much for the introduction, and I would also like to thank the organizers for inviting me here to Bristol. It's my first time, and it's very impressive how you managed to organize a full week of sunshine in Britain. It's very nice coming out of Germany and going into the sun. Yeah, so my group does slightly different work from the impressive work that you have just seen from Nam's group. We also work on superconducting detectors, but we're not so much interested in providing these devices as a standalone measurement system. We rather try to use them directly integrated in nanophotonic circuits as an on-chip platform. So packaging is not so much a problem for us, but on the other hand, it means that our detectors would be very helpful to use for anybody else that is not working with such circuits. Yeah, my group moved recently to Munster 2 years ago, so probably not many people know where that actually is, so I thought I'd draw you a small map. We're actually located in northern Germany here, in the middle of nothing. It's about half an hour away from the Dutch border. Historically, Munster is quite an important city. That was where the peace treaty for the Westphalian peace was signed some years ago. It also gave the Dutch their independence as a sovereign state. Yeah, history repeating, I guess. They were also able to leave the Francophonian Empire then. Yeah, Munster has a castle, as many German cities, and as also many castles, it's occupied by administration. They rule us with an iron fist. We have a nice lake here where you can go ice skating in the winter or sailing in the summer. And what you also see is one of the many churches in Munster. There's actually more than 80, and they have a saying that it either rains or the church bells are ringing, and if both happen at the same time, you know it's Sunday. We also have a nice city center where the peace treaty was signed. The university is actually quite large. We have 46,000 students and also 3,000 students in physics, so it's a relatively large department. We are somewhat a bit out of the city center in the Center for Nanotechnology. It's an interdisciplinary research center shared between physics, chemistry, and biology. And actually there's a lot of construction around it. On the left side, near the Max Planck Institute, we have a big construction site where we'll build a multi-scale imaging center, which is very nice for detector work because then we can directly cooperate with biologists and try to image their cells at low intensity. So we're excited about that. We'll hopefully be finished in 2 years. And on the other side, there's also a big construction site for this Center for Soft Nanoscience. Nobody really knows what this soft nanoscience is supposed to be, but it's a good name. Important for us, it houses one of the clean rooms. It's actually here, buried in the ground, and there's a big hump of earth on top of it for climate stability, and also for noise isolation, which is very nice. And that's actually almost finished, so we'll move in there next summer. Yeah, nanofabrication is very important for my group. We build all our devices ourselves. Our primary tool is the E-beam, and we're fortunate to have our own E-beam in my group. It's a 100 kV EBPG with a 100 megahertz clock, so it allows us to write very large chips on high speed and also make complex devices. So we've developed this programming language for writing with the E-beam over the years to build these type of circuits, which we call nanophotonic circuits. So they're kind of waveguide devices, but also combined with freestanding structures and electronics. Those we write with the E-beam and then dry etch. So fabrication is relatively straightforward. We do that on purpose so that the device yield is high and it's also relatively reproducible. These are the type of circuits that come out of it. This is an optical image of a part of one, contains many coupled interferometers and a bunch of detectors here on the top. So joint hybrid nanophotonic device if you would like, but the magic really happens at a much smaller scale. So it's transferable to a range of materials. We work a lot with silicon, which was also mentioned before. Silicon is a very nice material because it's highly established in the photonics community. You can make very compact devices, have very tight confinements, and that is also good for placing superconductors on top of it because they interact strongly with the propagating light fields. We do also a lot with silicon nitride if we want to work in visible wavelength regimes. This is particularly interesting for imaging applications. If you think back to the biologists, they have markers that fluoresce somewhere in the visible, so we would like to detect those, and that's not so good on a silicon platform, but the fabrication is very similar. And other nitrides we try also, like aluminum nitride. This is a wideband semiconductor, and it's interesting because it has a second order nonlinearity, so you can also make electro-optically tunable devices or use the piezoelectric effect inherent there. Common among all of these is that they are cavity devices, and they contain also freestanding mechanical parts. So if you look here, we have a circulating electrical field in the slot ring resonator. It's actually two rings inside each other, and there's a little gap in the middle that you can see here. And that freestanding bridge then works as a mechanical resonator that is also driven by the light field. So it detunes the cavity resonance a little bit, and therefore gives us an additional mechanical knob for adding reconfigurability to photonic structures. This also works on this microdisc. It's basically a freestanding wheel that is attached here at the center, and then the circulating power basically blows up this little wheel. It gets larger and smaller, therefore also changes the resonance, but at much higher frequencies in the gigahertz range, or multiple gigahertz if you do it right. The resonator is of course relatively large, has a large mass, but this can be fixed with this photonic crystal structure. Here the mechanical resonator is inside this little cavity and have very short beams. Also we make these one-dimensional photonic crystal where the entire beam is basically vibrating. Well, why I'm telling you this, we heard a little bit about phase shifters, and since we work at low temperature, we are not so fond of these thermal microheaters, because they don't interact very well with our detectors. We spend a lot of effort making the device cool, and then heating it up again with a microheater is not so perfect. So we like to go a different route with our mechanical devices. And this works quite well because they are essentially size matched. So these freestanding structures are waveguides and mechanical resonators at the same time. So if we move them a little bit, they change the optical properties of this device. This, for example, is a tunable attenuator. If you move one of these beams down, slightly layer intensity goes to the other side. You can also use that for changing the resonance frequencies in these cavities as before. This would be another design where the cavity is the mechanical resonator at the same time. I get a little disc and this micro pedestal which changes the frequency. And then we can take all of this and embed them into nanophotonic circuits where we can do further signal processing and actually get rid of some light that we don't like. So this is one of these filter stages that we've developed, cascaded Mach-Senders and ring resonators to also get rid of a pump light with the spectrometer at the end so that we can actually separate some wavelengths. Okay, yeah, but this was all driven by optical forces. This is not so good. We can also work electrically. And one particular phase shifter that we like is this electro-optical, optomechanical structure. It's kind of hard to see, I'm afraid. But basically we have a set of electrodes here for driving the resonator. Maybe if we zoom in a little further, you can see it better. It's basically an interferometer, and at the side is kind of this H structure that was developed in Hong Tang's lab at Yale still. So basically we have our optical waveguide. Attached to it is a second waveguide in the evanescent near field, so they basically form a slot waveguide. The optical light field is propagating this way. So essentially if you change the width of the slot, you change the refractive index and therefore induce a phase shift. And you can control this phase shift by pulling on the left side with these electrodes. The nice thing here is that it's a capacitive driving, so we only apply the voltage, but there's no current flowing, meaning that there's also no dissipation, and therefore the substrate doesn't heat up. The other nice thing is that this can work at high frequency, so typically these devices are in the megahertz range, but you can push them to much higher frequencies if you make it a little stiffer. Okay, yeah, but I actually wanted to talk about detectors. So now we'll add those to the entire circuitry, and you've already seen that the superconducting nanowires are very, very nice devices. They are the detectors, the tungsten silicide detectors made from NIST with over 90% efficiency. We worked with niobium nitride in collaboration with Gregory Goldsman's group in Moscow. They basically grow all our films. They also try to sell those. They have slightly lower efficiency, about 80% or so. Or we also worked with niobium titanium nitride, which single quantum also sells with even slightly lower efficiency. There's a few options. They're basically continuous films that we get from Moscow. Then we use our E-beam to structure them into nanowires, typically about 100 nanometers wide or so. And then we try to integrate them with our waveguide devices. So these layers are very, very thin, 3 to 4 nanometers. Here's, it's also hard to see, an actual device that you can buy underneath this optical fiber, which is glued with this big patch of epoxy here, is sitting on a sapphire substrate with 3.5 nanometer of niobium nitride on top. Technically, you should be able to see that it's fully transparent. It's actually very hard to image these detectors because they're too thin. But essentially, the coupling comes from the top, so the light is going through the detector and hopefully absorbed by the nanowire. You have to increase the rebound rate a couple of times with the cavity to increase the absorption efficiency. But for us, this is not very good because in our devices, we do not work out of plane, but everything is done in plane. So therefore, we do not want to have these types of devices, but rather integrate them directly on a waveguide. And this essentially started a couple of years ago, 2011, were the first two papers, one from Würzburg's group, working with 3.5 semiconductors with niobium nitride on top of it in a meander structure, and more or less at the same time there was also the TES waveguide integrated detector from the NIST group, which has the additional feature that is number resolving, which is very nice. Niobium nitride detectors that we use are just threshold detectors, so they're not sensitive to photon number. We built a similar device on a silicon wafer, so a SOI structure with niobium nitride loop on top. And later on, these designs have evolved and are now becoming more complex, also including photonic crystal cavities for localizing the light field. The benefit of these waveguide detectors is that now we are not limited by the thickness of the material anymore because we're not shining from the top, but rather we are absorbing in the propagating light field. So the interaction length is actually not the film thickness, but the length of the nanowire. And this, of course, you can make as long as you like, in principle, by design, if the E-beam doesn't have any stitching. But with some work, it doesn't. So that means that essentially all of the incoming photons can be absorbed by the nanowire, and assuming high internal quantum efficiency, that also means that the number of photons that are detected when they're propagated in the waveguide can be very, very high. We have moved away from silicon to silicon nitride, also using films from Moscow. We use relatively simple fabrication. As I mentioned, it's basically 3 steps of lithography. We first design the electrical contact paths, which are also creating the alignment markers for the subsequent steps. Then in the second step, we write the nanowire and etch the superconductor away where we don't like it, since our entire wafer is usually covered with a superconducting film, which comes from Moscow. So we separate material development and fabrication. And then in the last step, we actually write the waveguide structure using this photonic programming language that I showed you. On each chip, we have a lot of detectors then, since it's more or less scalable fabrication. Between each of these 2 contact pads sits a superconducting detector, and then on the input side we have optical access and electrical access from the backside. We put that in a cryo system and then measure one detector after the other to characterize the entire structure. So a standard system looks like this. Oh, hard to see. Basically, we have grating couplers that we use for getting light into the chip. This is our input side. We then split the light field into 2 arms. One arm goes to the detector. The second arm goes to a reference port. The length of these 2 arms is basically quadratically increased so that the absorption losses are the same in both of them, and we can use that for calibrating the number of photons that we actually have inside the structure. So we measure the intensity outside here. We measure the intensity on the reference device. Then we know if we have a good splitter, how many photons are traveling towards the detector. And here we can then contact it and measure actually the detection of deficiency of such a device. The entire system is mounted on a cold stage, which is a very compact optical and electrical setup. So we have a fiber array coming from the left side here with multiple optical input ports. We have an electrical probe coming from the other side, so they're basically going head-to-head, always in a fixed distance. We find our device by aligning towards these grating couplers and then touch down with the electrical contact probe onto these pads to establish electrical connection, and then we can start counting once we send some light into the photonic circuit. And all of this is then mounted into our cryostat. Looks like this. We have a wet fridge with which most of the experiments have been performed so far. In there is quite a compact system with a very large probe. It's hard to get a compact probe with enough fingers that you can actually measure many devices, but in the end it fits somehow. We move our chip around with an attocube, and if you look from the top, you basically see this head-to-head architecture with the electrical probe coming from the left side, the optical axis from the other side, and then the chip is this gray area underneath, which always moves under the entire system. So we touch down, measure, go to the next one, and therefore are able to calibrate a lot of devices. So typical measurement looks like this. This is the on-chip detection efficiency, I have to say, so it's not the system efficiency. We have quite a lot of loss at the grating input, but we don't care so much because we can always crank up the laser power and then compensate for the loss. What we do care about, though, is how many of the photons inside the waveguide we catch. This is around 80% typically. We also have some measurements above 90%, but this is probably a more standard number that we reach. What's also nice is that we have a nice plateau here for 15-15 photon, and as Sabu already told you, that allows us to bias further away from the critical current at the region where the dark count rate is very, very low. So that means the noise equivalent power is very good. They have quite good timing resolution, so also typical values are below 40 picoseconds or so, which we get for these U-shaped meanders, and relatively short reset times because we only need a single loop across the waveguide. This makes the nanowire relatively short, therefore reduces the kinetic inductance. Therefore, the detector is also relatively fast, so a typical number is a few nanoseconds. That means that potentially they also work at very high detection rates. Okay, but we actually want to reduce the jitter and potentially make these detectors even faster, so we thought how we can do that. And the problem is actually that the nanowire is oriented along the waveguide here, so this is still a relatively long wire, some tens of microns in length. We thought maybe we can just turn it around by 90 degrees, and then we have a very short wire that is limited by the width of the waveguide, actually. That is just a few hundred nanometers. The only problem is, of course, now our interaction length is, again, very short, and most photons just propagate through. But this can be fixed nicely with photonics, so basically we put a back mirror here, then we get already twice the amount of photons on the front side. We add a second mirror on the input side and therefore generate a cavity which has to be designed somewhat carefully so that actually the light is absorbed by the superconducting nanowire, not scattered out of the structure entirely. But essentially it's a photonic crystal structure for which there are many, many designs that you can work with in silicon. The additional advantage is that these are relatively compact, so we have a number of holes that are drilled into the waveguides, making this quite easy in designing. Then there's a cavity region which we can pull apart and define the resonance wavelength. And we have a back mirror which we can make better to actually make sure that none of the photons leave on this end, but rather all stay in the cavity. Okay, here's a device that we picked. It's nice and black. We call it a bow tie detector because the actual detector looks a little bit like a bow tie. So this is the nanowire covered by the HSQ E-beam resist still, and then we widen it so that we basically do not detect, not sensitive to photon detection back here, but the sensitive area is just this little bridge where the superconducting nanowire goes across the waveguide. You can see that the front mirror is, has only a few periods, so it's a weak mirror and lets a lot of light in. The back mirror is much stronger, so it extends in the backward direction to basically reflect all the incoming photons. This limits the optical detection bandwidth, of course, to the cavity resonance, but it's a design parameter that you can work with. So you need to match your detector to your detection wavelength. The optical view is not too high, it's moderate, about 2000 or so is a typical value. This also comes from the fact that it's not under edge, but rather sitting on the oxide, so basically the trapped modes can also couple to the radiation continuum in the substrate. But what we care about is that the nanowire is very short, about 700 nanometers. Okay, so we plug that into our same measurement system as before. It's the design that you have seen previously, again with the calibration port, so that we know how many photons are actually traveling towards the detector. Here the design is now different, it's this bow tie architecture. Then we use a CW laser, attenuated heavily, that is in the range of on the single photon level. We control the polarization because these grating input couplers are only sensitive to one particular polarization, usually TE in our case. We calibrate the power on two ports, first on the input and then also on the reference port, that we have relatively good confidence of how many photons are traveling inside the circuit, and bias it at the right position and count the number of clicks with the detectors. So what we find on resonance is a detection efficiency of about 30%. This is maybe not so impressive, but you have to keep in mind that the scattering losses in this first design are still relatively high, about 50%. So if you take the two together, it's actually not too bad. That can be improved with better cavity designs, which we are working on using 2D photonic crystals. But what is nice about them is that the timing characteristics have become much better. So we fabricated two same sets of devices on the same chip. One are these traditional U-shaped devices, which are along the waveguide. Again, those have a decay time of a few nanoseconds. But now the bow tie detector is very, very short. So typical values are about 200 femtoseconds. And we also found some devices which are even shorter, 110 picoseconds, meaning that you can potentially count at very high rates. We did some high-frequency count rates. We have a picosecond laser with a ramp rate of 1.15 gigahertz. You can see that we easily reach that count rate. It's that right here because we cannot get more photons out of it. So if you find a faster laser, we can probably push that detection rate. If you just go by the count rate, we should get towards 9 gigahertz or so. Not that there's a source out there at the moment, which that would be useful for. But it's a nice system to play with. The timing jitter, unfortunately, didn't get much better. This is most likely due to latching, so we don't work close enough to the critical current, but at a relatively low bias point. Therefore, the timing error is still considerable. It stays at the round of the previous detectors at a few tenths of picoseconds. But this can also be fixed. Okay, what's interesting, however, about these wires is that the absorption of photons is very strongly localized in this little bridge across the wire. And this is interesting if you don't want to just detect single photons, but potentially multiple arrival of photons. And this also works nicely with the superconducting detectors if you play a little bit with the geometry and also with the biasing conditions. So as Wu told you already, the absorption of a photon creates a hotspot, and that size of the hotspot depends on the biasing current, and also the width of the nanowire has an effect. So if you bias it very, very far from the critical current, you can think about generating only a small hotspot, meaning that the superconductivity is not broken down completely, but rather you need the absorption of a second photon to actually break the resistive barrier. And this you can also see in the earlier papers from Boltzmann. If you look at the slope of the detection efficiency versus power, if you work in the single photon regime, then it's a linear scale. If you work in the two photon regime, it's actually quadratic, and so forth. So if you absorb higher numbers of photons, you just play with your nanowire width and your biasing region. And this actually works also nicely with these U-shaped meanders. So here's one set of measurements for 3 different types of detectors. A thin nanowire usually breaks down by the absorption of one single photon. So here we have a slope of 1. If you make the wire slightly wider, we can go from a single photon to a 2 photon detection regime, and if we make it even wider, to go to about 2 photons or even more. The problem here is, of course, that the photons have to be absorbed in exactly the same location, and this doesn't happen so often if your nanowire is very long. But with this bow tie detector, they always are absorbed at the same location because they are propagating parallel to the waveguide, so this happens much more frequently. And that allows us also to see much higher photon coincidences up to a slope of 7 here. Of course, this is at a very, very low biasing regime, but nevertheless, this can be pushed again by the cavity design, playing with the width, and therefore also increasing the likelihood of absorbing multiple photons at the same time. So we think this might be an interesting direction for making threshold detectors that are not sensitive to few single photons, but rather higher number of photons at the same time. Okay, another nice aspect of this platform is that it's more or less scalable. So if you can make one detector now BQIT, you can also make many detectors. So a device that you can think of is this on-chip spectrometer. Basically, we take an input signal and then split it out spectrally into different waveguides. And then at the end, we could place a single photon detectors at each of the output arms. And this is exactly what we fabricate here for a device with 8 superconducting detectors. This is an arrayed waveguide grating as one option for doing waveguide splitting. At each arm, we have a superconducting nanowire made from niobium nitride sitting on top of the waveguide. This is silicon, so that silicon nitride, so that we can also work in the visible wavelength range. Then we wanted to see whether we can actually resolve some images, not with very high spectral resolution, but at least at different channels. For that we built a confocal setup where we have a sample here that is excited. We pick that up after driving it in the green wavelength regime, collect the light, couple it into an optical fiber, then it goes into our cryostat, again with the reference port. It's spectrally split into multiple waveguides, and then we measure at 8 different detectors at the output. And our particular emitter here is a cluster of diamonds which have silicon vacancies, so that they emit around 740 nanometers. We made 2 sets of devices because we can calibrate much better at 1550. So this is the first spectrometer with a C-band with 8 channels. Does more or less what you expect from an interferometer. Each of those is measured at the single photon level. The overall efficiency here is 20% for photons on chip. So again, quite lossy from the external side, but okay on the internal side. And then we look at the diamonds. This is a fluorescence map of them. And then if we pick one particular element here, you can actually reproduce the spectrum more or less looking at these 8 individual waveguide channels. Of course, this doesn't have very high resolution, but this is just a design parameter. We have only 8 channels, so if we have very high resolution, then we can only look at a very limited wavelength range where you don't see very many spectral features. So therefore, it's quite broad, about 6 nanometers per channel, but this is, as I said, a matter of design. Okay, and another interesting thing that we can measure with the devices are on-chip sources. I guess I have to be a bit quick here. Basically, we are interested in collecting light that is inside the waveguide. So one emitter that is nice is a carbon nanotube sitting directly on top of the waveguide that emits straight into the waveguide because it couples directly in the optical near field. And then we can measure that light that is emitted using our detectors. I'll skip this. So what we basically built is a very, very simple circuit, but the nice thing here is that it's all electrically connected. So the source is driven by current flowing, so it's basically impact ionization that creates photon pairs that are then emitted in the electrical near field of the waveguide. Because it's so close to the surface, most of the light actually couples into the waveguide with more than 60% coupling efficiency. And we have 2 detectors on the left side and on the right side. So basically our waveguide itself is a beam splitter, and we only need 2 detectors. We could also do with 1 detectors, but these CNTs are actually have a very short lifetime, therefore it's a bit of an issue. This is the actual device with several optical calibration ports for measuring the efficiency of the detector on the left side and on the right side. This is the drive for the carbon nanotube sitting here in the center. Then we have 1 detector measuring photons going to the right side, the second SSPD measuring photons going to the left side. As I told you before, they have a timing jitter of about 40 picoseconds, meaning that the system jitter of this entire structure is about 60 picoseconds. And this is an issue because the lifetime of the carbon nanotube is about 80 picoseconds. If it's sitting on the waveguide, making this whole measurement quite tight, it's not so easy to actually see the G2 dip. But we can see it, so these are some results that just go below 0.5. It's close, but at least it's non-classical. And as I said, the main limiting factor here is our detectors. They have to be improved in terms of timing jitter. This is also why I'm very interested in these really short detectors, which potentially could have higher timing resolution so that we actually can look down here all the way to 0. What's nice about the CNTs is that they have relatively high emission rates. This is the efficiency plotted here on the order of 10 to the minus 4 per electron, which is actually quite good for CNTs. But it means that the count rate that we get here in the region where we get a good G2 function is on the order of a few hundred kilocounts, which are the raw counts. not corrected for the detector efficiency or the coupling efficiency, so they are actually quite bright. And you can tune the emission wavelengths by playing with the chirality and the diameter of the wavelength. Okay, that brings me to the end. I have to thank, of course, the people that do all this stuff. This is not me, but rather my group here at some canoeing event. And as you see, it's not too large, but it can still grow. So if you're interested in doing your postdoc, we'll be happy to look at your application. And with that, I thank you for your attention.
Thank you, Wolfram. That was very nice talk. And time for questions. Back there, please.
I'll ask the same question maybe two different ways. What are the opportunities for pushing some of your designs into a professional foundry service, or how long before I have a building block in a foundry service to stamp out superconducting detectors?
In principle, we use standardized elements that we have optimized, but they're also available in foundry services, of course. So we could send all these devices to a foundry, but the turnaround time is very long. So we much prefer making these circuits ourselves, because then we have a new chip every other day, essentially. And that allows us to go through designs very rapidly and improve the structure. But once the actual circuit itself is optimized, this could be directly transferred. We don't use any special processes, but rather fairly simple elements that are also available at Epics Fab or whichever one you want to use. Sorry, what was your second question again?
How long before it's a building block I can use in a foundry service?
It depends on the complexity. So the simpler structures are more or less optimized, and those could go out straight away. Others are more exploratory, especially if you think about these mechanical structures. Those you don't get in the foundry service, but you could post-process it and do the wet release or such. Other than that, I think it's really nothing special. So we borrow a lot of designs that have been around in the photonics community for a long time and just use them in different directions, work in combination with the detectors. The SSPDs, of course, you also would have to do afterwards, since they are not available in the foundry, but this is in principle possible.
For the photonic crystal design, if you put the nanowire across the waveguide, do you see a loss scattering?
Yeah, so the scattering losses at the moment are about 50% or so. So
how much of it is coming from the interface of the detector and the
it's not so much the nanowire, because it's very, very close to the surface. So the coupling is more or less adiabatic. You can also tweak that a little bit if you kind of make a loop kind of structures, like a little hook across this, then you might maybe get some current crowding. But the stronger point is basically the side arms from the cavity, which we need for connecting the detectors, and those cause a lot of scattering. This is why we are trying to use these 2D photonic crystals, where you have confinement also in the lateral dimension, so not so much out-of-plane scattering, and that also in the simulation looks much better. So there the absorption goes above 90%, and with this design the maximum theoretical absorption is 50%.
Time for one last question. Up here.
Well,
Need the mic. Sorry.
I was just wondering, what are the challenges when it comes to applying your system to do photon number resolving detection? Or is it a better sort of platform for that, or is it a worse one?
So the pseudos number resolving detector, which we can implement, is combining multiplexing with many detectors. So you can make an array of splitters and then terminate each one. And if you make many of them, that in principle is a good approximation. It's not a real number resolving detectors, because you still rely that your photons distribute evenly. To directly measure the energy is very hard. I don't think that is realistic, at least not in the short term. But with this multiplexing approach, I guess you can come close. Making many detectors is not so much an issue. It's more the electronics of connecting many of them and then running the entire system at low temperature, because you have so many RF lines going down to the chip.
Thank you.
Okay, so I think it's time to thank again Wolfram, and questions will be accepted, I guess, a couple of time later. Thank you very much.